All right, hello everybody. Welcome to EEE 135. This is chapter 3, Solar Voltaics, where we are now on the second part of our weekly session. Last time we talked about PV cells and their design and kind of how to bridge them together to make one module. Here, we're going to talk about solar modules as the base building block and then go bigger and bigger until we start designing site-wide solar array systems, right? All the way from 10 kilowatts on your house to 10 megawatt solar stations that the utility owns. Okay. So let's go ahead and get started. First thing we need to look at is a solar module. This is typically the unit that you're going to purchase whenever you're designing and specing out data. In the electrical industry, we don't really buy individual cells and piece them together. If you work for the solar industry, a manufacturer, you would, but you typically design that all in-house and then put it all together as a package unit. So what you would buy if you're working for electric utility, or you're working as a consultant, you would just buy a straight up solar panel, right? Or we call it a solar module here. Right. You can also buy these off of Amazon as well. So you literally just go to Amazon and look up solar module, and then there's all sorts of different versions of them. They're typically like about, I don't know, cheapest one's probably like $300, all the way like $600. So it can vary on the performance and how much you want to pay and all this other stuff. So the key aspects you would use for the electrical data, because we're doing electrical design, will be the peak power. This is P max. So this particular PV module they use as example in the book is 215 watts. The rated voltage is 30. The maximum power point or the rated voltage is 39.8 volts. So it's almost 40 volts. Rated current for the whole setup is 5.4 amps. So obviously you have some in parallel, some in series to make this 39.8 volts and 5.4 amps. Okay. Now, this is a rated power. So a rated voltage, rated current, we get rated power. So we want to always operate at this range. Ideally, we try to. If for some reason something happens, we have to operate at a higher voltage, we're going to get less power, but we can go all the way up to a open circuit voltage. This is the maximum voltage the the solar module could ever put out, and that's 48.3 volts. But remember, open circuit voltage, we're not pushing out any current, so we're not operating effectively. On the other end of the scale, we have short circuit current. So if for some reason our voltage collapses and we're pushing out maximum amount of current, we're going to get a little bit more to about 5.8 amps. It's not that much more from 5.4, and our power goes to zero. So obviously operating in these edges is not economical. You want to operate at the rated values. Okay. Rated voltage, rated current will give us our 215 watts is what we expect from this solar module. Key electrical design, we need rated voltage, rated current. That's for the system design, right? And then from that, we could find our power. We also need to know the rated current for sizing conductors and fuses as well, right? So you're gonna have cabling, fuses, all this other stuff to carry the power from the solar module all the way to the inverter, and we need the all current to size all that stuff, okay? Now that's electrical data, mechanical data. This will still be an issue, right? So first thing, typically tell you how many cells we have. So this thing has 72 monocrystalline solar PV cells individually, right? Front glass is high transmission tempered glass, so it's going to let the sunlight through. You have a junction box. So here is kind of saying this is a connection style to connect your cables, right? Output cable is this MC4 connectors, a 1,000 millimeters length, and then that gets connected to the other device like a combiner box or an inverter. The frame is some type of aluminum for lightweight, and the weight itself is about 33.1 pounds. The big things that are going to be really important is the weight and the dimensions. It doesn't specifically say here, but it was going to tell you your length times width times height. Okay, length and width are the biggest ones because that's how big the solar panel is to place on your roof. Weight is a very big issue because your roof can only hold so much weight before it collapses. So you need to make sure that you're not going over the weight capacity. You also need to make sure you're buying enough you're buying an adequate amount of solar modules to put on your roof. You don't want to buy too many and then realize you don't have enough roof space and then you kind of screwed yourself. Okay. Cable management wise, we got cable connections. We're going to go buy spools of wire and then splice them and connect them. We have a junction box to kind of put all together, put some fuses, maybe some disconnect switches in there for safety. All this has to be done by a NEC standard, the National Electric Code standards for solar panel installations. So you can't just do DIY whatever you want. I mean, I guess you could. You're going to be out of compliance, and I'm sure your insurance, homeowner's insurance will go bonkers, and it'll probably void your claim whenever they realize that. So all else being equal, you really should follow the NEC code. If you don't know what that is, you really should be hiring a qualified electrician to do it. Okay, so it's up to you if you want to get into the actual cable management side. I'll tell you as an engineer, typically engineers design things on computers, on paper, on drawings. They don't typically go out and hardwire stuff. That's for the electricians' work. The electricians and engineers work side by side. The electricians are typically the hands-on type of person that ends up wiring everything together. The engineer is more of the design aspect where we're building a whole system that's larger sizing devices. And then we're telling the electricians, hey, wire this thing to that thing and giving them drawings. Okay. So typically you're gonna work together side by side with an electrician and you guys will both figure out what are the correct cable, junction boxes, all this stuff until you end up memorizing NEC code yourself. Okay. So just to give you an idea, terminology, so you have solar modules and then solar arrays, right? Some people might say PV modules as well. I think it's kind of interchangeable. Solar modules, remember, combined. So solar modules are single solar cells we put together to make a single panel, right? So solar module, solar panels, kind of same terminology. You combine multiple solar modules together to make a whole larger installation, and this installation is called a solar array. So a single cell goes to a panel. This panel is what you buy, and then you can multiply it into whatever type of, series versus parallel to whatever size you want. But typically the solar panel is what you buy. You just buy 9 of them, and then you will wire them up however you want, and that's your solar array. So an array is a combination of panels. Typically your house will have one solar array. So example, a house might have like 15, 20 solar panels on top of it. You wire them all up to one inverter. That's a solar array system. Okay. Solar arrays are then the next building block to then build your systems. Again, residential for your rooftop, you're just going to have one solar array because it's typically 20 of them is one solar array. Commercial, this is more like hospitals, the university, Sac State has solar panels on top of the rooftops. Amazon warehouses have solar rooftop. And then you have parking lots that have the cover for the car so your car doesn't bake in the sun. Those covers typically have solar panels. Well, I think Walmart has some of them here in Sacramento. Okay, so commercial, you're gonna have multiple solar arrays. Think of like a maybe the parking lot. You have one row of cars. You're gonna have one row of solar panels. That whole row might be one array, and maybe we have 10 rows, so we're gonna have 10 arrays. Right, so it's not a hard stop how many is in an array, but there's typically, like I said, somewhere around 20, 30 or so. You don't want to get too big. Okay, but commercial, you definitely see multiple arrays because it's going to be a lot bigger than residential. Utility scale, this is where we're talking about powering up a whole neighborhood, not just a Walmart. And we're talking megawatt level, and we're talking thousands, probably tens of thousands of panels. That's then hundreds of solar arrays. We even group solar arrays into clusters and sectors to then stamp out across the land. We might be using 100, 200, 300 acres of land to make a utility scale solar generation site. Okay. And just to give you an example, 1 acre typically, I don't know, Sacramento, 4 houses is typically you could put on 1 acre, maybe even 6, depending on how compact they are. So just remember, 1 acre is 4 houses. You put 100 acres, that's 400 houses. 400 houses is a gigantic neighborhood, just to give you a scale of what we're talking about. Okay, we're going to go through each one and show you a design example to see the number crunching for all 3 levels. Because if you're going to be electrical engineer and design side, you're probably going to be designing one of those 3, if not all of them, depending on what company you go for. All right, so let's start with the basics. Solar array design. We got one PV module or solar module. We could then take it. We need to ask what's the rated voltage, the rated current, and the rated power. Then we could start making our system. Remember, the first step is take the single building block, put them in series to create the voltage that we want. So first, step number one in the design process, put solar panels in series to raise the voltage to the desired specs. And we'll call this a string. This would be a solar panel string. After we have the solar panel string, we could then copy and paste it in parallel to increase the current and increase the power. So we have a 4-panel string here. We want double the power. Well, sorry, it's kind of weird, this one. Let's say we have a 2-panel string, right? So here we have 1, 2. So we got 2 in series, another 2 in series, another 2 in series, another 2 in series. So in this case here, they kind of redistributed a little bit. And then we have a 2x4 setup. Okay. But that's the idea, is you just keep on building it. It's like Lego building blocks. You get bigger and bigger and bigger until there's a limit, right? For safety reasons, we probably don't want to go over like maybe 20 panels in an array or something. And we'll talk about why. But it's the same logic as we did last time with the cell. We're just building it up, okay? So first off, let's talk about residential solar arrays. So we have our solar panels on the rooftop. There's so many, there's obviously so much rooftop space. We can't put them everywhere. So we put however many we can. Okay. What's the typical load demand for this type of load in this sector, the residential sector? So typical house, you want to have about 10 kilowatt power ratings for your solar panel, right? That gives you a little extra energy for the inefficiencies of the inverters and the systems. You might want to charge your batteries for a night. So you want to kind of supersize your system. 10 kilowatts is a good starting point. It's a good average. If you want to be really cheap, you might go down to 5 kW, but you're not going to be self-sufficient. You're still going to be buying power from the utility most likely. Okay. So that's the typical load you want to power in your house. So again, when you install your solar system, start with 5 kW. That's a small system. You could go up to 10 kW if you want to fully power your house. Okay. Some people try to think it's an investment where you can make a really big system and sell energy back to the grid when you have too much. That's kind of a misnomer. Some utilities do it, but nowadays in 2025, they're kind of streaming back on that. Like I heard San Diego Gas Electric kind of reverse that decision. I'm not sure what SMUD is doing, but not many utilities are letting you sell energy back into the grid, right? There's a whole host of issues and safety concerns, and people trying to game the system. It's a big headache for utilities, right? Especially when people think that, oh, you're not paying me the same rate I'm selling it. So of course, of utility, I'm not going to give you the same rate I'm selling it to. I'm gonna buy from you for less. Okay, the reason why is I could buy energy on the market for like 6 cents a kilowatt hour. I'm not going to buy energy from you for 12 cents a kilowatt hour. That's stupid on my part. I'll be nice and buy it from you for 6. But then as a customer, you're like, well, why are you charging me 12 when only paying me 6? Right? Well, that's just how the market works, dude. So people don't want to, utilities get so tired of arguing this type of stuff, is don't be surprised as whatever utility you end up being in your new city, when you go get a job, they'll say, no, you can't sell energy back. So with that being said, it's typically better to match your residential solar array to your house load, or less if you want to save money. Don't do more. You're just wasting money, in my opinion. Okay. So here's a good example of speccing out a typical solar array for your house. So let's design a relatively small 5 kW solar array for residential rooftop solar installation. We have a solar module from the previous slide. Rated voltage is 39.8 volts. Rated current is 5.4 amps. The power of one module is 215 watts. So let's go ahead and build our array system. For safety, typically want to keep any solar array voltage below 50 volts. OSHA has a rule that anything 50 volts and above, it's going to be too dangerous for regular consumers to use. Right? You ever wonder why, if you ever go to your 117 lab, you really can't get above 50 volts on your function generators and whatnot? It's because 50 volts is the maximum where, hey, if you get shocked by 50 volts, it's not going to seriously hurt you. It might be a little painful, but you're not going to die right then and there. Okay, so it's just as a safety thing. Anything above 50 volts, you really should be a qualified electrician to start touching it. right? No one, I don't know how many people actually follow it, but that's the actual rules. So follow the rules, make it below 50. So first thing is, let's look at the voltage. We literally say we have to be less than the maximum voltage, so equal or max of 50 volts. So we have V times the number of modules in series. This would be 39.8 volts. Well, we can only put one. If we put two, it's going to go up to 80. It's going to be too much. So it's very easy right now, just literally one module in series. So basically, we're just going to take individual modules and now put them in parallel. So step number 2, we want to parallel the solar module until we meet the power requirements. So remember, one module is 215 watts. Well, we want 5,000 watts total. So our maximum power needs to be 5,000 or more. Okay, we don't want to under-design the system. We could go a little bit over to make the customer happy. Okay, so the power of a string, which is just one, is 250 watts. We will multiply that by the number of solar panels we want in parallel. So for 5 kW, it'd be greater or equal than 215 times X. X needs to be 24, right? You can just number crunch it on the calculator. So we need 24 modules in parallel. So literally each one, there's nothing in series besides the individual one. We're just taking them all and just paralleling them down the line, okay? So kind of what it would look like. So let's summarize the design. So we need to purchase 24 modules in total to have an array, a power of the array of 5,160 watts, or 5.16 kW. So we're going to buy 24 modules, get this done. Array voltage is 39.8 volts, right? And this is kind of set up, one module in series, 24 in parallel. So here you can kind of see electrically we draw one. This is kind of like the symbol for circuits of a solar panel. Right, so it's a box with like a V shape in it. We're going to have them all in parallel all the way up to 24, and we're going to come out to 2 DC terminals for V out. Okay. So that's kind of how you design it. A third step I didn't really put here is you would typically want to look at what's the total current, the size of conductors, but we'll talk about that later. Okay, so that's residential. We go ahead and look at commercial solar arrays. So typical, we talked about a Walmart. You got solar panels on top. You got the parking lot with the overhangs, they have solar panels as well. So what's a typical load demand for the sector? I mean, that could be as small as 50 kW for like a grocery store, all the way to 1 megawatt for those giant Amazon distribution centers. So it could get pretty darn big. 1 megawatt is a lot of power. Okay, you could probably a whole neighborhood takes about 1 megawatts worth of power. So that just shows you, think about your entire neighborhood versus one Amazon center. Okay. So what's a typical installed power capacity you want to install for this commercial sector? Is I've seen typically 100 kW or more. Anything below 100 kW, it's kind of like, is it worth the time and to pay a consulting firm to design everything? So I've seen 100 kW or more, right? Typically, you're going to have under 1 megawatt because you just, at that point, you don't have enough physical space to install it. Right? I mean, 1 megawatt takes probably acres and acres. It's probably like, what, thousands of solar panels, right? You just physically don't have the room on your rooftop to do it unless you got a really, really, really big building. So it's very rare to see anything over 1 megawatt in the commercial sector. Okay, so let's do another example problem. Here is going to design a commercial solar array system. All right, so let's design a relatively small one, a 100 kW solar array for the warehouse, rooftop solar installation. Okay, now we're past the everyday me and you touching voltages. We could go more on the industrial side. So let's say we could limit the solar array voltage to about 1,000 volts or less. Okay, so that's, higher voltage is good in the sense that we could be more efficient because we're running less current, less losses, because power is always I squared R losses. But we don't want to go too high with voltage because then it's going to be too expensive for the inverters and the installations to be too big, right? There's a good middle ground. So it's just in commercial, industrial aspects, about 1,000 volts or under on the DC side is a good medium of efficiency versus cost of the expensive high voltage equipment. So still have the standard solar module again from supplier, 39.8 volts, 5.4 amps, 215 watts. Let's build the system. So first off, Let's get that. Let's get right under 1,000 volts. We get higher efficiency. So at 1,000 volts, we have to be less than or equal to that. Our module voltage times the number of modules in series would give us our answer. So we are 1,000. We have to be less than or equal to 1,000, where we are 39.8 times X. Where we can number crunch this is 25. So 39.8 times 25 is 995 volts. So we're right under that threshold. Good job. Okay, so we're going to have 25 modules in series. Okay, and that's the string. Now we could go and start asking, well, what's the power of an individual string? 25 is a lot. Okay, so the power of string equals each individual modules multiplied by the number of modules in that string. So the string power is 250 watts times 25, or 5,375 watts. So that's one very long string. Okay. Now we could then take that string and we could copy and paste it over and over again to increase the power to 100 kW. Okay. So our total power of the entire array should be 100 kW, and we need to be equal to or greater than 100 kW. That's why I have the equal greater sign. We have an individual power of the string of 25 solar modules is 5,375 watts. Now the question is, how many of those we need to put in parallel? Remember, we take that long string, we copy and paste it over and over again until we eventually reach that 100 kW level. So we have 5,375 watts times X equals to or greater than 100 kW. Do your calculator, X is 19. So to be exact, 5,375 watts times 19 is 102.1 kW. So that's a whole power of our entire unit. Okay, so we're going to put 19 solar module strings installed in series. So the question is what does it all look like? Well, the array is going to be 25 by 19 modules. So we're going to put 25 in series, and then we're going to parallel them 19 times to get our total output voltage. Okay, our total power of the system is 102 kW. Our voltage is right under 1,000 at 995. I didn't ask us this, but I would say, what's the total number of modules we have? I got my calculator. 25 by 19 is 475 modules. Okay, that's a lot. Almost 500 solar modules that we installed on the rooftop. Okay, so you can see commercial solar arrays, they could get bigger and bigger and bigger. And I can imagine, if you think of the rooftop, maybe this string right here, that could be one little layer on the rooftop. And they put another layer and another layer, and they could just go down on the roof all the way across the warehouse. Okay, if you ever go look at satellite view, you can see how they kind of group up these solar panels. Look up here. You see how we have this group right here? This group could be one set. This could be another. This could be a third and a fourth. Depends how long this line is, right? You also have over here, there could be another group. Look up on the rooftop. You see how that kind of grouped up together? That's kind of how they, depends how many they're having in series versus parallel. They could make little bundles to save on the wiring. You don't want to split them all far apart on the rooftop, because then you get to buy extra wires to put them all together. Okay. Now on the rooftop, they might not be this exact perfect, 25 by 19 box, but it'll be pretty close. Okay. So that's commercial level. So let's go ahead and take our break right now. We're going to take that 15-minute break. I want you to do an exercise. I want you to design a commercial solar array. So let's make a little smaller, scale back one so the numbers aren't that crazy. I want you to design a 50 kW solar array for a small warehouse rooftop solar installation. Now, as an owner, I say, I want you to only limit to 600 volts. I think 1,000 volts is a little too high for my safety standards. Let's go limit it to 600. Give me a 50 kW system and just tell me what it looks like. Design it for me. Your supplier has the same PV solar module with 39.8 volts, 5.4 amps, and 215 watts. So I want you to find, number one, figure out how many solar arrays in series to get right underneath that 600 volts. What's the power output for each individual solar array string? And then number two, parallel them up till we get that right at or above 50 kW. And then kind of summarize for me what the design looks like. Okay. So good luck with everybody. We'll come back in 50 minutes to see how you did and check your design. All right. So Take it easy for a little bit. All right. Oh, hello everybody. Welcome back to EEE 135, Chapter 3, Solar Voltaics. Here we're going to continue from our break. We were talking about an exercise where I wanted you to design a small commercial solar array. So design a 50 kW solar array in a warehouse rooftop solar installation. Make sure we stay at or below 600 volts and make sure we go above to meet our 50 kW power requirements. So let's see how we did it. Step number one, always look at the voltage first. So go ahead and say we need to make sure we're less than or equal to 600 volts. So we have a 39.8 volt solar module. So how many of those we put in series to make sure we get closer to 600 volts? So it's 39.8 volts times X equals or is equal or less than 600. Calculate it out, it's 15. So we need to put 15 modules are installed in series to make the solar array string. The exact voltage is going to be 59.7 volts if you multiply everything out. So next question is, we know we have 15 modules in series. What's the total power of the string? So string power is going to be the individual solar module of 215 watts multiplied by 15 modules in series. You get 3,225 watts. Okay, so that's how many we have. The PV module in series is a net total of 3,224 watts. And we just copy and paste that down the line, put them in parallel, and we get our total power. Remember, total power needs to be greater than or equal to 50 kW. Each individual string of solar modules is 3,225 watts. We got to multiply that by the number of strings in parallel to get our net power. Do a number crunch, we have to multiply by 16 to get a total of 51.6 kW, which is right a little bit above our 50 kW threshold, but that's what we want. So take the 15 string modules in series, that's the string, and then copy and paste it 15 more times and put them all in parallel. So at the end of the day, we have a 15 in series by 16 in parallel array. And the total net output power is 51.6 kW with a terminal voltage of 597 volts. And then you can send it to the inverter and the rest of the system. So if I take 15 times 16 is about 240 solar modules purchased in total. Okay. So that's kind of like a small design that you would a quick rough estimate of what you would do. So yeah, that's solar commercial power. Let's go even more large scale to utility scale solar arrays and systems. So this is kind of an image of a solar station where you have thousands and thousands, not 10,000 solar modules. And if you literally just take that same module design we've been using and just making it bigger and bigger and bigger and bigger and just copying and paste the design as many times as you want. Okay. So what is a typical load demand for this sector and a utility level? Our loads are typically considered either distribution substations to feed our neighborhoods around us or industrial sectors. Like you might have an oil refinery, you might have like a Tesla battery factory, you might have an Intel laboratory, right? So there's different levels of loads, but in general, you can expect a substation to be somewhere between 10 megawatts up to 100 megawatts. Now, I know technically SMUD had these little mini substations that are a little bit less, but we're talking about across the United States. Typically, substations are about 10. The smallest you'll see really is 10 megawatts. Otherwise, it's not worth the millions of dollars to build a substation. Up to about 100 megawatts. Anything above 100 megawatts, you're better off splitting off the substations because it's going to get too much. It's going to be too much equipment. It's going to be too big of a single point failure. You're better off just building two substations nearby and splitting the power if it gets above 100 megawatts. Okay. So anywhere between 10 to 100 megawatts is our typical load. So then we need to, if we're going to somewhat even get in a ballpark, we need to make sure our solar arrays nearby is somewhere between 1 megawatt up to about 50 megawatt installation. So that's a typical utility scale. Basically, it's not worth building anything less than 1 megawatt because the cost it takes to get the land, all the regulatory things. building in remote areas. You have to build this is a mini substation next to a solar array. There's a lot of capital costs involved in building a utility scale solar plant. You want to make sure you get your money's worth. It has to be at least 1 megawatt, in my opinion. Right? Typically go up to about 50 megawatts. Anything above that, again, it's going to be too big. You're better off just building 2 separate sites. Okay. Just to give you an idea, something around this area, this plant right here, this uses up 600 acres of land. That's a lot. Okay, that's like an entire zip code worth of land for some areas in Sacramento. Okay, I can imagine probably all of Midtown and downtown put together. That could be about, it's probably more than 600 acres, but you're not too far off. Just to give you an idea. Okay, so these are big, really, really big in terms of land usage. All right, so let's go ahead and see the design aspects. We're so big at this point, we're not even going to focus on the individual module anymore. We're gonna say we have a set solar array of 35 modules, and we're just going to start that with the building block. For example, if you look at this picture up here, you see how we have all these rows and they're identical everywhere? Each row is a row of 35 solar modules. And we're just going to use that as the smallest building block. We're going to copy and paste that over and over and over and over and over again. Okay. So not even go down to individual module level. We're going to start with an array. And this array is rated at 1.39 kV. The rated current is 5.4 amps and is rated at 7.5 kW. Okay, so that's the total amount of power that this row of solar modules will produce. So let's take that and then we could put that in parallel and series, all that good stuff to eventually get that 10 megawatts. We got a long distance to go from 7.5 kW. Some design limits. We want to limit the solar cluster to only about 10 arrays, and we don't want to go above 1500 volts. Now, we're already at 1.3 kV, so that's pretty close. In terms of clusters, let's go back up to this picture. You see how they kind of block everything off? There's going to be kind of little blocks that you don't want to get above so many, right? Otherwise, it's a little harder to kind of piece out and say, hey, this is one sector, another sector, right? We don't want to just put all of them in one row all the way down and have them unmarked. So in general, we again want to get that modular design. So let's cluster this up to 10 arrays into a cluster. And once we have the cluster, we could copy and paste the cluster over and over again until we get that 10 megawatt level. Okay. So let's start with the cluster. We want to put 10 of these arrays together, right? So first off, voltage-wise, we're not gonna put any in series because we're already close to that 1500 volts. We are running at 1.39 kV or 1390 volts. So these are all being parallel. Now we could put a max 10 array. So let's go ahead and do that. Each one 7.5 kW. So a cluster is 75 kW. Okay, so one cluster we plop on the ground. Think of it like a little square of 10 rows. That's one big building block, a cluster, 75 kW. Okay. What's the output of the solar cluster? So remember, there's 10 of them. They're all in parallel. So each one's 5.4 amps. Multiply them together. So each cluster is 54 amps. 54 amps is kind of a lot. All right. So just to give an example, your house, the main breakers and the main feed coming to your house, depending on the style, if it's on average somewhere between 100 to 200 amps. Okay, so typical house, I'd expect it taking about 100 amps maybe, and that's you're doing a lot, right? 50, 20, 30 amps is probably what you expect to be drawn from the grid. So 54 amps is pretty much a household's worth of current just from that one cluster. Okay, just to give you an approximation what 54 amps looks like. All right, so we have a cluster of 75 kW. Now we copy and paste that over and over and over again until we get 10 megawatts. So now we have 10, our design has to be above 10 megawatts, so greater or equal. Our cluster is 75 kW. How many clusters do we have to eventually get that 10 megawatt level? Okay. So 75 kW times X has to be equal to or greater than 10 megawatts. You do number crunch is 134. So you need 100. You take that little square cluster, copy and paste it 133 times more on your plot of land you purchase over and over and over and over again. And you'll eventually get to 10.05 megawatts, which you can round it to about 10 megawatts or 10.1 megawatts if you want to get a little extra on your piece of paper. All right. So in the end of the day, install 134 clusters, put them all in parallel because we don't want to get above that 1,500 volts, right, to the connection point. Now, one thing to say, when you build a cluster of 10 solar arrays, typically we'll take that, put that into one wire, and that one wire running 50 amps will then typically be connected to an inverter or some other device, and that's going to then get connected to the main power grid through a substation. Okay, so again, we like building blocks. So 134 is a lot, but we parallel them all together, and then eventually with a lot of wiring, a lot of nodes of connection, we'll get to the main transformer at the substation. We'll convert it. So sorry, somewhere we have to convert DC to AC, give it to the step-up transformer, and it goes to the transmission grid. Okay. So kind of summarize your design. The site has 134 clusters with 10 arrays each, which is equivalent to 47,000 modules. And your total output power is 10.05 megawatts. Okay. I don't know about you, but 47,000 is a lot. That's like warehouses full of modules. So just think about when you order a module, Amazon comes in your box in your front lawn. Just remember that at utility level, we're ordering almost 50,000 of those and just littering the landscape with them. Okay, that's how you make solar utility scale solar sites. Okay. So those are the three major design points, starting for residential, commercial, and then utility. They all share the same logic of building voltages, building up power ratings, figure out your current. It's just how big you want to get, right? Utility scale, you just have a couple extra steps to get your bigger and bigger building blocks, but the basics are all the same. It's all circuit analysis at the end of the day. Okay, so we have the electrical side all stamped out. We have the solar panel lined up. The next major thing we need to do is cable management. We have to get the power from the solar array eventually to the inverter or whatever power electronic device we use to either convert it to AC for the power grid, or we store it in the battery or use it directly. But there is going to be a power electronic module, a controller somewhere. We need to wire our solar panels to that. Okay. How do you do that? Well, one way you could just throw wires on the ground. That's a terrible idea. So typically, we have many solar modules and arrays. We need to have some organized effort to keep track of wires and cables, and this is called cable management. Okay. So the idea is you have a certain a string of solar modules. They're typically in series. You're going to have a cable that comes out right here. This cable is going to go to a combiner box. So for neatness, we route all cables and wires through a combiner box. In here is kind of the node that we make the parallel connection. So notice we have one set in series that has one point up here. This is the parallel connection. We have another set in series and a third set in series, and they all come right here. And this is the actual parallel point. Notice that there's these little squiggly lines before each one. Those are called fuses, right? We want to put protected devices in case something goes wrong. There's too much current. We don't want to burn up the solar modules. We don't want to burn up the combiner box of the wire. So we put these safety fuses in case there's an accident, it'll burn up and disconnect automatically. Okay. So combiner box is literally a metal box you can open and close. There's probably a lock on it so random people can't steal the stuff. But you open it, you'll see a bunch of wires bolted up to a metal strip. And then you'll have little slots you put your fuses in. Okay. And it's nice and neat. The combiner box is weatherproof. It's all perfectly lined up. So there's no mistaking what's what. It's really, in my opinion, cable management, it's all about neatness and organization. Just so when you see it, you're like, I know what we're doing. There's no guesswork. We're not going to touch anything stupid. Okay, so that's cable management, very, very important in solar panels and solar array systems. And this is all governed by the NEC. right? So they have a combined, there's an approved combiner box set, like different manufacturers, but they all have different combiner boxes, but they all follow a very specific standard that is the exact same size and connections and all this stuff. So they all should be roughly equal. Okay. So that's kind of the major pieces on how to start building and designing your utilities scale, commercial scale, residential scale solar arrays. We've been talking so much about PV modules and the monochrome crystalline modules and the silicon and all that, but we really should pay a little respect to other types of solar modules and other ways to get electricity from the sun. It's not always just silicon-based PV panels. You can have other ways, right? One version is concentrating photovoltaics, CPV. So a more advanced PV cell design is a concentrated version, which uses mirrors and lenses to focus sunlight into a single PV cell. Now, normally what we've been doing is we take one PV cell and just copy and paste it about 90 times to make a panel, and we just lay it on the ground or the roof, okay? And we have a decent amount of sunlight hit it. Somebody said, why don't we take a mirror or like a magnifying glass and focus all the sunlight in a big area into one tiny 6x6 square? And just make sure this PV cell is ultra high efficient. We're going to spend $1,000 to make this one PV cell the best thing possible, so that we get a giant area of sunlight all focused into one little PV cell, and we get the most amount of power out of it. That does work, right? The more sunlight is concentrated, the more photons, the more electrons get knocked out. You're going to get more power for sure. Okay? There's several different ways you could do this. You could use a conventional lens like a magnifying glass to focus the beam. You could use something called Fresnel lens, which is kind of like, instead of making one giant concave lens, it's a bunch of smaller ones. It's thinner, but it still focuses all the sunlight. So here you have the lenses. Look at the yellow part. You see how it's focusing all into a single PV cell down here. Now, one bad side about this is that thing is going to get really hot, like really, really, really hot, because you're focusing all that sun on it. So you're going to have a giant heat sink, some liquid cooling behind it, something to make sure the temperature doesn't melt the whole thing. Okay. Another way to do this is using mirrors and reflections. So you have the sunlight hit a kind of concave mirror, and it's going to reflect all the sunlight into this one PV module. So sorry, let's say the sunlight comes up here from the top. It's going to hit this dish. Is then going to focus on this middle lens area, which will additionally reflect again back into this telescope, into this tiny little lens right here. Okay, so it's all about playing with mirrors and just aiming everything in the correct orientation to get a bunch of sunlight into one small little area. Okay, here's a reflection disc. You can see this little bent area. This is all mirrors. It's not PV panels. And they're all reflecting it into this one little bucket up here, and that's where the little module is. Okay. Here's this Fresnel lens, is all right here. So all this, you can't see, but behind it, it's going to all focus into one little solar cell about right here in the middle. Okay. Now, sounds cool, but there is one very important part that the regular silicon panels don't need. It needs to be directly facing the sun at all times. Because you're looking at mirrors and you're focusing on one little point, if the mirror gets bent like 5 degrees away from the sun, the reflection, you're going to totally miss that tiny little 6x6 square. Okay, so that's a big crutch of the system, is we need to constantly move all the lenses and all the mirrors to be pointed directly at the sun at all times. And that's a very big ask. You see a solar panel you put on your roof, once you install it, you forget it's there for the next 6 months. This device needs daily babysitting. Something needs to move it every minute, and just throughout the whole day, have a mechanical system move it as the sun goes from the east to the west. Okay, that takes a lot of effort. That's exactly what we're going to be talking about next week. We're going to talk about how to track the sun, how to get these specialized solar systems to always keep going with the sun to get the maximum amount of power. Okay. So, in summary, today, what did we learn about renewable energy systems? We mainly talked about solar PV systems. Solar arrays are modules. So solar arrays are made of individual solar modules that we stack up in series and parallel to get a larger power level. Okay, so remember, we start with a PV cell, that's all manufactured into a module, and then the module gets copy and pasted about 20 to 30, 50 times to get the whole solar array for like a household. Okay. There's 3 sectors we design solar arrays for, typically residential, and then we could go bigger from solar arrays to solar sites for commercial and utility scale. There's 3 major levels. You might be working for one of these, you might be working for all 3. So for me, I work at Turlock Irrigation District. I'm a utility level. We're actually having a project where we're building solar panels and canals. This is a utility scale project. Okay. Electric design process typically follows. You look at the series, you take modules in series to increase the voltage to the desired voltage needed. You call this a string. And then you take the string and you copy and paste it in parallel over and over again until you get the desired power, and that's your output module. Okay. Sometimes you might have to do this again and again if you're getting to the utility scale level, because again, we're always going for those modular designs. We could just take a small thing, copy and paste it over and over and over again until eventually we have the biggest system possible. Okay. It's all about repeatability. Just make your life easier. Okay. Lastly, we talked briefly about different types of other types of specialized solar generating systems. They're called concentrated photovoltaics, CPV. These very specialized systems where you take the sunlight, you focus it into a very small, highly efficient PV cells. You typically use mirrors or lenses, some type of optical system. Of course, the big crux of all this is these systems need to always directly aim at the sun at all times. So we need solar tracking systems. Again, that's what we're going to talk about next week. Okay. So with that being said, I want to say thank you for showing this week and listening to us talk about how to build the solar panels, modules from the PV cells, modules to arrays, and ultimately designing systems for residential, commercial, utilities, right? Go out there. This is the type of stuff you're going to probably use for the rest of your career if you're going to be in the solar industry. Okay. So hope everybody has a good week. We'll come back next week and pick up more for the solar tracking part. Other than that, guys have a good day. See you around.